In our previous lecture, we talked about notion of stability for time-varying systems. So far, we have only dealt with autonomous systems or time-invariant nonlinear systems. And in the previous lecture, we extended the notion of stability and also asymptotic stability to the more general case, where the right-hand side is allowed to depend on time also. Okay. T. Now, with that also generality, suppose that the origin is the equilibrium point of whose stability properties we're interested. And the standard definition of stability, which we made use of for autonomous systems, is still valid, we saw, for the more general non-autonomous case, okay, which was for each epsilon, okay, positive, there exists a delta, okay, such that if you start in the delta neighborhood of the origin, you always remain in the epsilon neighborhood for all future times, okay, for all t greater than or equal to t0. And by future times, we mean times larger than initial time t0. Okay. Now, there's one thing that we have to be careful about this definition when the right-hand side is time varying, and that thing is that suppose that epsilon is given, it's fixed, and I find a delta that for which this definition holds today. Okay, but tomorrow the same delta may not work. The reason is that the right-hand side depends on time. Okay, so therefore this delta for time varying right-hand side is not only a function of epsilon, but in general, function of the time from which you start the system. Okay. Now, it's usually desirable that for design, let's say, it's the same delta holds for a given epsilon. The delta holds all the time. Okay, or delta just the same delta works for all times. Okay, and that motivates. So from that point of view, this definition or this behavior that delta depends on time is not good enough. Okay, so that motivates to introduce a stronger version of stability, which is called uniform stability. Okay, so this is stability, and by uniform stability, what we mean is that this dependence on t0 is now absent. Okay, if that's the case, then that's a stronger version of stability, and that's called uniform stability. Okay, that is for each epsilon there exists a delta such that when you start in delta neighborhood of the origin, you remain in the epsilon neighborhood for all initial times and for all future times. Okay. If that's satisfied, that is, if delta is independent of t0 the initial time, but only depends on epsilon, and that stronger version of stability is called uniform stability. Note that for a time invariant right-hand side for an autonomous system, those two definitions are equal. They are the same thing. Also, we extended this uniform stability way of looking at things to the asymptotic stability. Also, okay, we had the standard asymptotic stability, which holds also for time varying systems, non-autonomous systems, and we also introduced uniform asymptotic stability, which, generally speaking, means that if the convergence rate doesn't change with respect to initial time, then asymptotic stability is uniform, we said, for an autonomous system. Today we will provide a different characterization of uniform stability and uniform stability. Instead of using epsilons and deltas, we will use the so-called comparison functions, and through them we will give equivalent definitions of uniform stability and uniform stability. And those definitions are more useful in general when we're doing nonlinear analysis, okay, for dynamical systems. Okay, so we begin this lecture, therefore, introducing the so-called comparison functions, okay, through which we will try to understand uniform stability and uniform stability. They're very simple and general functions. They're defined from R to R. They're scalar functions. First, we begin with class K functions, a continuous function call it alpha. Defined from the positive real line to positive real line is said to belong to class K. Okay. And sometimes this notation is used, alpha belongs to K, if it's strictly increasing and it starts from the origin. If it's strictly increasing and it's 0 at 0. Okay. A little bit stronger definition gives us class K infinity functions. Okay. What we require in addition to these conditions is that the class K infinity function raises unboundedly. Okay. As its argument goes infinity, its value should also go to infinity. Okay. Let alpha be a class K function if alpha s grows unboundedly as its argument does, then such a function alpha is said to belong to class K infinity. We write alpha in K infinity to mean that. Clearly, if a function is class K infinity, it's automatically class K, but not vice versa. You know that this set is a subset of class K. And then we have KL functions. Okay, and that's the third and last function in our list. A continuous function beta 0 infinity to 0 is set to belong to class KL. Okay, we use same notation as before. We write beta in KL. If, no, that beta, the class KL function, it has two arguments. and it behaves in one way with respect to one of its arguments, and it behaves in another way with respect to the second argument. And how it behaves is as follows. If for each fixed time, or let's say t bar, okay, the function we fix its second argument at some value, which we call t bar, and then consider that as fixed. Now this becomes a function of a single variable, okay? The argument b, or the variable b, the first argument, okay? And then when that function, if it's a class, it has to be a class k function in order for beta to be a class kl function. So this is class K, and when you do the reverse thing for each fixed S bar, the first argument, the function beta S bar, that is now we're fixing the first argument, and then second argument is allowed to change, and this becomes a function from half real line to half real line. And that function must be non-increasing, meaning that it may be constant every once in a while, okay, but it can never increase, but it's allowed to decrease. And it should every once in a while decrease, so that as time goes to infinity, it reaches 0. Beta S bar t is 0. Okay, that's class K function. Let's provide a few examples. Okay. For these function classes. Examples. S0 alpha S. Okay. S equals some positive constant times S, for instance. This would be the simplest class K function, okay? A line with constant slope. So this alpha belongs to K, and since it's increasing unboundedly, as S goes to infinity, this goes to infinity, it also belongs to K infinity. Now here's an example where it belongs to class K but not class K infinity. 0 S alpha S. Here is somewhere where we converge to. Consider something like that. Alpha S equals 1 minus e to the minus S, for instance. It's 0 at 0, continuous, and strictly increasing. But strictly increasing doesn't mean that it grows unbounded. It may be converging somewhere. So still, this is a class K function. Okay. Now this alpha belongs to class K, but it does not belong to K infinity because its increase is not unbounded. Is a family of examples for class KL function. Okay. So here we have something like that, and here we have okay. So let this be beta of S1 comma t. the one below the S2, comma T, and the third one be some other S fixed, and then we look at its evolution with respect to time. Okay. And such a behavior, for instance, can be realized by S squared e to the minus t. Okay. It should be decreasing with respect to its second argument when the first argument is fixed, and it should be increasing when its second argument is fixed with respect to its first argument. So this is a class scale function example. Okay. Now, using these very general and simple functions, we will now redefine uniform stability and uniform asymptotic stability. Okay? So we will get rid of the epsilon delta in our definitions. Here's an alternative definition to uniform stability and uniform asymptotic stability. Okay. This lemma establishes the link between the old definitions and the new definitions in terms of new class K and class KL functions. The equilibrium of x that equals f of tx is, okay, remember what we mean by equilibrium for an autonomous system. So if this is an equilibrium, it means that the plug-in x equals 0 here, and for all times t, right hand side is 0. If that's the case, then origin is an equilibrium point. Okay, so equilibrium, suppose that for a given nonlinear system, non-autonomous, origin is an equilibrium point. Such equilibrium point is said to be, or is uniformly stable, if and only if there exists some class K function and a constant, positive constant C, both independent of when we might start the system, and is independent of the initial time, such that x t0 being in the C neighborhood of the origin implies for all future times norm of the solution is always upper bounded by the initial norm passed through class A function for all t greater than equal to t0. So that's uniform stability. Okay, now then instead of epsilon delta, now we're using a class K function. And we're using the term if and only if, therefore, if this condition is satisfied, then the epsilon delta definition holds, or if the epsilon delta condition holds, then you can always find a class K function and a constant C such that this condition holds. Then we have uniform asymptotic stability if and only if. Again, we have equivalence. There exists class KL function beta and a constant C both independent of the initial time. such that suppose that, provided that you start close enough to the origin, then you always, or the norm of the solution is always bounded by a KL function in the following sense. Okay. X t0, norm of the initial state is the first argument of our KL function. Now that it's increasing with respect to the first argument when the second argument is fixed. Okay. And the second argument is how much time has elapsed from the initial time. Okay, so the difference between t minus t0 or all t greater than or equal to t0. Okay, that's uniform aspect stability. And finally, globally uniformly aspect stable if and only if there exists data independent of the initial time this time we have no, see, we don't have to start close to the origin. Okay, so this relation holds for all initial conditions, such that norm is upper bounded by the beta function of initial norm and how much time has passed. This is x of t0. For all future times. Now let's also introduce one last and the strongest type of stability, namely exponential stability. Okay, that's our final definition. Equilibrium x equals 0, the origin of the system x that equals f of t x is said to be exponentially stable if exists positive constants c, k, and lambda, such that for initial conditions close enough to the origin, okay, norm of x t0 less than c implies that the norm of the solution x of t is upper bounded by a very special KL function, which is one where it depends linearly on its first argument and exponentially on its second argument, minus lambda t minus t0. Since lambda is positive, this means we're talking about exponential decay. Okay, and the overshoot is a function of, or the max motion is a function of the initial, linear function of the initial condition only for all. Okay. And finally, we can say stability is, or exponential stability is global if we don't require the initial closeness of the state to the origin. Okay. And globally, exponentially stable if we can let C equals infinity. Okay. Or in other words, if we can let this condition drop, that is, this holds for all initial conditions. Okay. Now, in our next few examples, we will try to emphasize that there is actually a difference between stability and uniform stability, or a spherical stability and uniform spherical stability. For that, we're going to make use of time-varying linear systems. Here's an example from the book. Example 417. Consider the following. First order LTV system, linear time varying system. X equals some function of time times the state x. So that's the definition of a linear time varying system. 6t sine t minus 2t times x. This is the first order linear time varying system. Okay. Now it's easy to integrate this, and we can write the solution explicitly, which is x of t equals the initial state times e to the integral of that time varying A matrix A of t. Okay, so exponential 6 the solution is x of t equals x of t0 times exponential 6 sine t minus 6t cosine t minus t squared minus 6 sine t0 plus 6 t0 cosine t0 plus t0 squared. Okay. This x means e to the that argument here. Okay, so t0 is the initial time and t is the time after t0. And x0 is our initial condition. So let's call this function g. Okay, clearly it's a function of both initial condition, initial time, and the current time t. And let g bar be, it's a function of the initial time t0, and we define it as max t greater than or equal to t0 g of t0. Okay. Okay. So first of all, it's always fixed t0, it always has maximum, because what happens is, even though some funny things may happen, eventually everything will be dominated by this minus t squared term, and it will be equivalent, it will be approximately equal to e to the minus t squared. And that's a function that decays quite fast towards 0. Okay, so it may do something funny for a while, but eventually its tail has to goes to 0. And since it's a continuous function, somewhere it has to reach its maximum. And from that on, it can never be as high as that. Hence, this g bar is a well-defined function. Then, for each given t0, g bar of t0 is some finite positive number. And that allows us to see that this system is stable according to epsilon delta definition. That is, you give me an epsilon, I can always find a delta such that after a while, or if the initial condition is not larger than delta, then I always remain less than or equal to epsilon. Hence, given any epsilon, a positive number, we can always choose delta as epsilon over this positive, probably very large number. Okay. Note that this number, well, in a sense, it's the maximum overshoot. This maximum overshoot depends on the initial time where you start your system from. Therefore, delta depends on where you start your system from. Okay, t0. And with this delta and epsilon, we can now apply the epsilon delta definition to see that the system is actually, or excuse me, the origin is stable. Okay. So x t0 less than delta, which is a function of t0 because of that dependence, implies the norm of x of t less than or equal to g bar t0 minus x t0. Okay, now that, take the norm of both sides, well, this is always positive. Norm of x of t equals norm of x t0 times that function of time, which is positive. Okay? So clearly, norm of x of t can never exceed norm of x t0 times the maximum value that this function can attain. Okay? Hence, the norm of x of t is less than or equal to g bar t0, defined here, times the initial norm, x of t0. And that's less than or equal to what? G bar t0, okay, times this, we upper bound by the delta that we have chosen. And delta we have chosen is here, epsilon over g bar t0. Now these two g bars will cancel, and we have epsilon here. Therefore, initial state starting in the delta neighborhood of the origin, okay, guarantees that we never leave the epsilon neighborhood. But the catch here is that this delta neighborhood depends on the initial time from which you start the system, t0. Anyway, so for epsilon and t0, we can always find a delta, and we have this epsilon delta condition satisfied. Therefore, according to our definition, the origin of the system is stable. The origin, therefore, is stable. Now, it's worthwhile to ask, okay, it's stable, but is it uniformly stable? Is the origin uniformly stable? And it turns out that it's not. Okay? So let's see how. How about uniform stability? Now, remember, uniform stability is such that you give me an epsilon, okay? For each epsilon, I can find a delta, such that this delta will work for all t0, okay? Now, this delta that we have used, that we have chosen, is a function of t0. The question now is, can we find a delta which is independent of t0, and this condition, epsilon delta condition, works for all initial conditions? The answer turns out to be no, and here is why. For t0 equals 2n pi. Okay, now we consider a family of initial times, okay, which are even multiples of pi. And then we're going to consider a particular time in the future. Note that this should hold for all times larger than t0, but now, since we're trying to construct a counterexample, just one time in the future is enough to violate the condition. And that time that we want to pick from the future is pi seconds later than t0. Okay, so t therefore is 2n plus 1 pi. Okay. Now for this t0 and t, and here we have the explicit solution, we can write, we have x of t equals x t0 and exponential. Okay, because we're very careful about the times being multiples of pi, the sines and cosines will be zeros and ones in a nice way, and we can simplify this expression here into the following: 2 4n plus 1 times 6 minus pi times pi. Okay. Now, this guy, okay, what we're trying to do is we're trying to figure out some delta that would work independent of t0. Okay, so in this very special example, that would be a t0 that would work, a delta that would work independent of n. Okay, because we define t0 as a function of n. And then this we require to be less than the given epsilon. Okay, now for simplicity, since we are trying to find a counterexample, all we need is a single instance. Suppose epsilon is 1. Okay, epsilon is unity, that's given. And for 1, epsilon equals 1, I want to figure out a delta, I want to find a delta, such that if the initial condition is less than that delta, then for all future times, x of t is less than 1. Okay, and that delta should work for all initial conditions. Okay, or in other words, for all initial time, or in other words, for our counterexample, for all n. But it's clear that, so this is 1, for simplicity we took epsilon equals 1, and now we want to find something very small, let's say, so that no matter what n you choose, this is always smaller than 1, this x of t, or this product. Now, no matter how small you pick delta, it has to be, first of all, by definition, it has to be something positive. It's very, very tiny, but no matter how tiny it is, you can always find an n large enough so that this tiny number times this large number is larger than 1. And at that point, the epsilon delta condition breaks down, and it shows that delta should always depend on t0, and we cannot have uniform stability. So, given epsilon positive, without the subjectivity, you can just take epsilon to be 1 because we're generating a counterexample. There is no delta. You can never find delta small enough that works for all t0. the origin, even though it's stable, it's not uniformly stable, is not uniformly stable. Okay. Now, in our next example, we will this time show that uniform. We can find a system for which the origin is asymptotically stable, but not uniformly asymptotically stable. That's our next example. It's example 418 from the text. Another linear time varying system. X equals minus 1 plus t times x. And so that we're considering times that are possible. The solution, once again, can be exactly written down, is x of t equals initial state times state transition matrix, okay, for the time varying matrix, which turns out to be 1 plus t0 over 1 plus t. Now, is this system uniformly, is the origin uniformly stable? Okay. That is, for each epsilon, can I find a delta that's independent of t0, such that solutions starting in delta neighborhood remain always in epsilon neighborhood? In this simple example, it is especially easy to pick the delta given epsilon. And it's clear that it would work for all t0. Note that at the initial time, so t is defined for times larger than t0. At the initial time, we have 1 plus t0 over 1 plus t0, that's 1. For all future times, this is smaller than 1, okay? Therefore, x of t, or normal of x of t, is always decreasing, okay, monotonically. Hence, no matter what epsilon you give me, I can always pick delta equal epsilon, and I will never be, I will always be in the epsilon neighborhood because the norm never increases. So the answer to this question, which is obvious from the explicit solution, is yes. Because x of t is never larger than the initial norm. Okay? The future norm is never larger than the initial norm. So that means I can always pick delta to equal epsilon. Okay, because it's a very special system. How about asymptotic stability? Okay. Well, the answer is again yes. For asymptotic stability, all we require is that we converge to the origin, provided that we start close enough to the origin. In this case, we don't even have to start close enough to the origin. All solutions converge to the origin, converge to 0. Why? Because this is fixed, because t0 is fixed once you start it, and as time goes on, the denominator becomes larger and larger. Therefore, this whole thing becomes smaller and smaller, and therefore, the overall product, which is xt, becomes smaller and smaller. So all the solutions are converging to the origin. Yes, because again, it's easy to see that this limit is 0. Now, how about uniform asymptotic stability? For that, we have to think a little bit And after that, we'll see that the answer is no. How about uniform asymptotic stability? Okay, here is the claim. The answer is no. Now, to prove our claim, which is that the origin is not uniformly asymptotically stable, suppose otherwise. Okay, that is, we suppose that the origin is indeed uniformly asymptotically stable, and then using the definition of uniform asymptotic stability, we will obtain certain conditions, okay, and those conditions will give us certain consequences, and then those consequences will contradict where we start from. Okay, so let's construct that counterexample. If the origin is indeed uniformly asymptotically stable, then by definition there should exist some constant c positive and some time or length of time interval that's large enough, let's call capital T, and that should be independent of, both should be independent of the initial time t0, such that xt0 smaller than c implies x of t smaller than d, okay, in the definition. But now since it should work for any d, we're dealing with, we're picking d equals c over 4. Okay. And for that d, we will have a capital T, and that capital T is here. Okay. For all t larger than or equal to t0 plus t. So that's uniform asymptotic stability for each c, and now we're picking one of those many possible c's, and we're picking c over 4 for d, okay, and then that we should have a capital T such that no matter where we start from initial time point of view, provided that we start in c neighborhood of the origin, and we wait long enough, by long enough we mean capital T seconds, we will always be in c over 4 neighborhood of the origin, if the origin is uniformly asymptotically stable. And now we're going to reach a contradiction from this line. Take x t0 equals c half. Clearly, c half is smaller than c. And since this should hold for all t0, choose t0 to equal to t, to capital T. Then, using the solution explicitly written over there, we can write the norm of xt evaluated at t equals t0 plus t. Okay. This is our future time, and we start at t0, and t0 is 2 capital T. So that equals x t0, 1 plus t0, 1 plus t0 plus capital T. Here we use the explicit solution. And that equals x t0. And now t0 is not an arbitrary initial time, but we let, okay, deliberately we let t0 to be 2 capital T. So we have 1 plus 2t, and here we have 1 plus t plus another 2t, so that makes 3t. And this is always larger than this norm times 2 over 3. And this norm is smaller than C over 2. Therefore, this equals C over 3. Okay. Now, what happened is the following. This should hold for all t0, okay, with fixed capital T, and provided that we start from the C neighborhood of the origin. So we actually chose the initial norm to be C over 2, therefore this condition is satisfied. Okay, we start in C neighborhood, and we chose the initial time. Since we can choose any initial time, this condition is initial time independent. We chose initial time to be 2 capital T, and capital T is how long we have to wait before we drop to C over 4 neighborhood of the origin. And we plug in those choices and evaluate the value of the norm of the solution in the future, which is T0 plus capital T. T0 was 2 capital T, so we're talking about the value of x of t at t equals 3 capital T. This is the solution. Okay, we plug in t equals T0 plus capital T, and then we plug in T0 equals 2 capital T, and we have 2 plus 2 capital T over 1 plus 3 capital T. And what we have is that this is greater than this. Okay, and this was C over 2, and that gives us C over 3. So if this is larger than C over 3, clearly it cannot be smaller than C over 4. Therefore, we have a contradiction. Hence, the system cannot be uniformly asymptotically stable. This contradicts with the condition star.